Alright, this video is on sampling distributions. Okay guys, the easy explanation for a sampling distribution is that it's very different than what a samples distribution could look like, okay, or what a populations distribution can look like. So think of a sampling distribution as what would many samples look like if all put together. So let's try to get an idea of what we mean by sampling distribution, okay? So first off, we have the population. Remember, the population is literally is a complete set of all the items of interest, right? So if our population was great white sharks, then the population would be every single great white shark in the world. Or if our population was United States citizens, then the population would be all United States citizens, okay? Now, a sample is just a subset of that population. So a sample is just hopefully a random sample, right, from that population that we hope to use to represent the population, okay? So from population, right, so in a population, we have a true mean. So think of that as the true average length of every single great white shark. Again, somewhere out there in the world is the true average of every great white shark, but we're probably never going to really know that. And somewhere out there is the, somewhere out there is the true standard deviation, sigma, right, for great white sharks. And we can also look at proportions as well. For example, if I'm trying to find the percentage of Americans that wear their seatbelts, somewhere out there is the true proportion, so I'll use a P, the true proportion for the percentage of Americans that wear their seatbelts. Now, in a sample, right, we just get a taste of those values. So they're not always going to be 100% right. So for example, we might just sample 10 great white sharks, and X bar would be the sample statistic for our sample, right? So we hope that it's close to the truth, but because it's just a sample, it might not be exactly the truth. We also have from our sample a standard deviation. S is a standard deviation. We hope that it's close to the true standard deviation, but it's probably not going to be very accurate. And again, if we're trying to get a sample of, say, I don't know, 100 United States citizens and what percentage of them wear their seatbelts, then we would get a p-hat. So a p-hat is a sample proportion, which we hope would be very close to the true p. So population produces what we call parameters. And like I said here, population parameters are fixed quantities. So somewhere out there is the true set average length of a great white shark with a standard deviation. Somewhere out there is the true proportion of United States citizens that wear their seatbelts. And samples create what we call statistics. And statistics may vary, right? They're not fixed. They vary. You know, my sample of 10 might come back with a certain average length for great white sharks, but you know what? Nicole down the street, she might do a different sample of 10 other great white sharks, and she would get a different average because they were a different group of 10 great white sharks. So the sample statistics vary because they're samples, right? Where the population remains the same. So the distribution showing how a statistic varies is called a sampling distribution. So a sampling distribution is the distribution. I'm actually going to try to write this neatly, but that's going to be debatable. The distribution showing how a statistic varies. So what we see in a sampling distribution is how a particular statistic, whether it be an average or a proportion, will vary from the truth. Okay? So there are two types of sampling distributions. One's for the mean and one for the proportions. Let's talk about each one of those right now. Okay? Now, the other important thing we have to understand is that the goal of any sample is to try to uncover the truth, right? I don't know the true length of a great white shark, so I'm going to try to look at a sample of 10 of them to try to uncover the truth, right? We hope that our average is close to the truth, but guess what? It's going to vary. And if I do another sample of 10 or another sample of 10 or another sample of 10 or another sample of 10, they're all going to be varied. They're not all going to be exactly the same. And that is what we call sampling error. Remember, sampling error is not a bad thing. It's not a mistake. It's simply the natural variation that occurs between samples. So let's talk about sampling distributions of a sample proportion. First off, for a sample proportion, we're usually talking about categorical data. So when we're looking at proportions, we're talking about categorical data. Okay, so usually the answer is a yes or no. Okay, for example, I might say, do you wear your seatbelt? Yes or no. So the response I'm getting back is going to put a X amount of people into the yes category and a Y amount of people into the no category. And I can create a proportion from that. So if it's usually something that's categorical, where your answer is yes or no, then it's going to end up being a proportion type problem. Okay, now keep in mind that when n is large, we can use a normal model. Remember, we want to be able to use a normal model to describe the sampling distribution for a proportion, but we do have to meet those conditions. Let's go through our conditions really, really quickly because they are important. We must have a random sample, and we must meet what we call the 10% condition. Remember, the 10% condition says that our sample, n, is less than 10% of the population. Okay, so if I'm going to look at 100 people in my sample to try to figure out who wears their seatbelt or not, 100 needs to be less than 10% of all United States citizens, which I'm pretty sure it would be. And number 3, don't forget that you need 10 or more successes and failures, and you need to show the work for that. Okay, guys, don't just say it. Now, think about a sample. Okay, so I'm interested in finding a sample. Okay, and I'm trying to understand what percentage of people wear their seatbelts. So, what do I expect my sample proportion to be? Right? So I haven't done the sample yet, but what do I think my sample proportion would be? Well, I hope that it is the truth. So I hope that I expect my true or my sample proportion, right? P hat's the sample proportion. I expect my sample proportion to be the truth. And what about the standard deviation? Well, the standard deviation for my sample proportion is going to be the square root, giant square root, of P times Q divided by n, and all of that is inside the square root. Just in case you're wondering, Q is 1 minus P. It's the opposite of success, right? So again, I expect my sample to be the truth, but it's going to deviate, and it's going to deviate by the square root of P times Q divided by n. Okay, and I'm going to explain where this formula comes from in class, but it's really an easy formula to work with. Okay, so now when I make my sampling distribution here, okay, and I'm going to draw my best normal model I can. Right in the middle, I expect the truth. Why would I expect anything else for my sample? But I understand that my sample could be off by 1 standard deviation or 2 standard deviations or 3 standard deviations. It could go down 1 standard deviation, down 2 standard deviations, down 3 standard deviations, right? So I certainly expect my sample, right, to fall somewhere in here. Now, as long as it falls between -2 and +2, right, as long as it falls in here, I certainly think that it's a normal sample. It would not be surprising to me, right? Any person's sample could vary, right? So let's say that somebody told me that 70% of people wear their seatbelt, right? Well, I could calculate the standard deviation. Again, the standard deviation would be the square root of 0.7 times 0.30 divided by my sample size. Let's just say I'm going to stick with that 100-person sample, right? I might come back with 71%. Somebody might come back with 69% or 68%, or somebody might come back with 73%. Again, the whole idea that samples are going to vary is called sampling error. It happens, but this is just representing what we expect many samples to look like right here. Now, if a sample comes back below -2, or if a sample comes back above +2, well, then we start to question that sample. We start to question whether or not what we thought was true, right, what we centered our distribution on, we start to think that that might be wrong, because again, we don't believe when rare things happen below -2 or above +2, okay? But that's the basic idea, right? Our p hat is expected to be in here somewhere, right? And remember, a sampling distribution represents what many samples would look like. And for any random sample, we expect it to be the truth, but we understand that it's going to deviate. Okay, let's look at a couple problems here and try to understand this. All right, first off here we have, suppose that 13% of people are left-handed. What could a sample proportion look like? Well, if 13% of people are left-handed, and I want to look at a sample, let's say I'm going to look at a sample of 90 people, right? What do I expect that sample proportion to be? Well, why would I expect anything other than the truth? If there's 13% of people are left-handed, I certainly expect to see 13% of people that are left-handed. But I understand that my sample, right, might deviate. And the standard deviation is 0.13 times 0.87, that would be Q, divided by 90, again my sample size, okay? And if I divide this out, so let's see here, I have the square root of 0.13 times 0.87 divided by 90, I get 0.0354, 0.0354. Okay, now, the first thing I want to teach you is this number right here, n, is really important. The bigger n is, the less your sample will deviate. And that should make complete sense. A bigger sample will be expected to be closer to the truth. So a bigger sample will deviate less. So that's why when you divide, you create your standard deviation to be smaller. Bigger sample size, smaller standard deviation. So anyway, this is what I expect. So again, I could draw a nice little picture of this. Well, not going to be real nice because I'm a bad drawer. But anyway, right smack dab in the middle is the 13% I expect. I can go up about 4%, up another 4%, up another 4%, down 1, down 2, down 3. Again, standard deviations, okay? So let's say we want to answer a question dealing with this, right? So again, our sample would be expected to be anywhere in this range. Anything below -2 or above +2 would be a little bit weird. But anyway, our auditorium has 15 lefty seats. In a class of 90, again, that's our sample size, right? The sample size we talked about was 90. What is the probability we don't have enough lefty seats? Well, let's see here. If my sample was 15 out of 90, right? So 15 out of 90 is 0.16 repeating. So if I did have 15 kids in there that are lefties, that would be 16 or about 16.66666, right, percent of students that are lefties. Well, I expect 13% of students, right? So let's see where this particular sample right here would fall in my sampling distribution. To do that, I'm going to calculate a z-score. I'm going to take the 15 out of 90. Now, the reason why I'm putting a fraction here, guys, is because I don't want to just round it to 0.16. I want to keep the whole decimal there. Minus, I expect 0.13. Divided by, well, again, I understand that everything's allowed to deviate, so my standard deviation for a sample of 90 would be 0.0354. Okay, so if I do that minus 13, I'm sorry, not minus 13, but 15 out of 90 minus 0.13 divided by my standard deviation of 0.0354, I get a z-score of 1.0357. 1.0357. So that would be about right here, right? About right here. Would be where I would have 15 out of 90 people, or a proportion of about 16% be lefties. Now, would that be weird? Well, no, it certainly wouldn't be. That is not an unusually high z-score, right? So if this actually happened, I would not be shocked. It would just be, hey, samples vary. It would be weird, right? So I want to find the probability we don't have enough seats. So we don't have enough seats would be anything higher than that, right? Because if anything higher than 15, no, I'm not going to have enough seats. I have enough seats for 15 or lower. Anything higher than 15, I don't have enough seats for. So let's see here. How do I calculate that? I'm going to use the normal CDF on my calculator. I'm going to go from that z-score of 1.0357 to 99. And I get that there is a 15.02% chance that I do not have enough lefty seats. Okay, so again, I took the 15 out of 90, and that was the 16% that my sample showed. And I found out that that's not really an unusual sample based on this model here. And I found the probability that it was higher than that, and that's where I got the 15.02%. Okay, so hopefully that problem makes sense to you. All right, I got another one over here for us to look at as well. Okay, now let's talk about the sampling distribution for a sample mean. The sampling distribution for a sample mean. Okay, now let's see here. Okay, first off, means are used for quantitative data. Quantitative quantitative data. So when you would use a mean, you must have actual numbers. You must have lengths of sharks that you're going to average, or heights of people, or weights of people. You must have numbers that you're going to average together, basically, to get a mean, right? Okay, once again, I'm going to say this again. Bigger samples vary less. A sample of 1,000 will have a mean closer to the truth than, say, a sample of 100, right? If the sample's bigger, we expect it to be closer to the truth. All right, now, we once again want to be able to use the normal model here. And in order for us to use the normal model, there's a couple conditions that we have to meet. The first condition is our sample needs to be a random sample. So just like before, that's not any different. Okay, we also need to meet that 10% condition. It's the same condition from before with proportions. My sample must be less than 10% of the population, and that kind of guarantees independence for me. And the third condition is a really weird one that we got to clarify by the end of this video, but our sample must be big enough. Now, what the heck does big enough mean? Well, I'm going to try to explain that, but basically, we want our sample to be big enough. What's big enough? We'll try to quantify that a little bit later, but we don't have proportions here. We have means, so we don't have successes and failures. So we don't have that 10 success and 10 failure rule. We just have this big enough rule, and I'm going to explain a little bit more later what that means. So just assume for right now that samples are big enough. Okay, so let's talk about our sharks, right? So if I'm going to take a sample of 10 sharks, what do I expect my sample to look like? Well, I would expect it to look like the truth. Why would I expect anything else? And what about the standard deviation for my sample? Well, remember, the key thing I said earlier, the larger the sample, the lower the standard deviation. The less you will vary. The closer you will be to the truth, the bigger your sample. So to calculate your sample standard deviation, you take the true standard deviation sigma and you divide it by the square root of your sample size. Again, I will explain a little bit later where that formula comes from in class, but it's the standard deviation from the population divided by the square root of the sample size. And again, as the sample size gets bigger, you're going to divide by a bigger number, which means your standard deviation will lower. Okay? So again, when I have my normal model here, right? I expect the true mean right to be in the middle. I can go up 1, 2, 3. I can go down 1, 2, 3 standard deviations. Once again, I really expect my sample to fall somewhere from -2 to +2, right? And it would not be surprising for me to fall anywhere in here. It would not be surprising because guess why? Samples vary, and that's called sampling error. It's just something natural that happens. I can't do anything about it. Now, if I fall below -2 or above +2, then I start thinking maybe this true mu was wrong, because there's got to be a reason. We don't just believe in weird things happening, okay? So let's try to do some examples here. Now, the key things I want to mention right now about the big enough condition is that as long as your population is normal, you could always use the normal model. I mean, remember, these conditions are aiming me to using the normal model. The reason why I check these conditions is because I want to use the normal model. So if your population is normal, then just go for it. But if your population is not normal, you do need to be big enough. And we'll explain what that means a little bit later here. All right. Suppose tomatoes weigh an average of 10 ounces with a standard deviation of 3 ounces. If we buy 12 tomatoes, what do we expect the mean to be? Well, let's see here. What do I expect my sample of 12 tomatoes to be? Well, why would I expect an average anything other than 10 ounces? If the true average is 10 ounces, then I certainly expect my sample to be 10 ounces. But again, my standard deviation is going to change here. Why? Because I have 12 tomatoes. I think I said apples earlier, sorry, tomatoes. So I'm going to take the 3 standard deviation that's true for the population, and I'm going to divide it by the square root of 12. So 3 divided by the square root of 12 is going to give me my standard deviation of 0.8660. Now, why? Well, remember, the reason why standard deviation is smaller is because for a sample of 12, we would expect it to be closer to the truth. It's very easy for one tomato to be very overweight or very underweight, but a sample of 12 tomatoes on average, right, on average, should be closer to the truth, right? So my sampling distribution would look like this, right? And right smack dab in the middle is the 10 ounces I'd expect, but I would be okay if it going up 1, 2, or 3, or down 1, 2, or 3 standard deviations, which is 0.866. That's what one standard deviation would be. And remember, I would certainly expect my sample to be totally normal if it fell anywhere from -2 standard deviations to +2 standard deviations. If it fell down here, I think that somebody might have been lying to me about this 10 number. And if it fell up here, I think somebody might have been telling a little bit of fib with that 10 ounce value. Because again, we don't believe in weird things happening. What should a sample look like? It should look like something that would fit into here. All right? So it's very easy to calculate those values. Very, very simple. Okay, suppose the total amount spent by student vacation for a week in Florida is $650. So, a lot of students go on spring break or something like that. So they expect to spend an average of $650 a week in Florida. But again, that number deviates. The standard deviation would be $120. What is the probability that a sample of 20 students spend a mean amount more than 800? Well, let's talk about what we expect. What do we expect for a sample of 20 students? Well, first off, I certainly expect that their average would be the truth. Why would I expect anything else than $650? If that's what the average is, that's what I expect. But my standard deviation is going to be a little bit different because I have 20 kids, right? And 20 kids on average should vary less. So I'm going to take the $120 that's true for the population and divide it by the square root of 20, my sample size. So 120 divided by the square root of 20 is 26.8328. Let me see here. That's 26.8328. And please get used to using 4 decimals for standard deviation. All right. So I could draw a nice, beautiful normal model here. Well, I don't know about beautiful. And right smack dab in the middle, I expect $650. I can go up 1, I can go up 2, I can go up 3, down 1, down 2, down 3. Okay, now, where does $800 fall into the mix here? Well, that's what I'm going to need a z-score for. But wait a minute, a z-score implies the normal model. Let me run through those conditions real quick. Hopefully this is a sample that's random. 20 random students. It didn't say that, but I just have to assume it. 20 students is certainly less than 10% of all students that go on spring break down in Florida. I'm sure of that. And I also have to assume that 20 students is big enough. Now we're going to find out that even if it's not, we're still okay. And I'm going to explain that shortly here. So what's the z-score for 800? Well, 800 minus I expect 650 divided by my standard deviation of 26.8328. So I get 800 minus 650 divided by 26.8328, and I get a z-score, get ready for this guys, a z-score of 5.5902. That is way over here, right? Impossible. So, well, I mean, I want to calculate the probability, right? So the next thing would be to go to normal CDF. It said more than 800, so I'm going to do a normal CDF from that z-score to 99, and the probability is, it's get ready for this, it's 0.00000000114. It's extremely low. It's not going to happen. But what if it did? What if this miracle did happen? Well, then this 650 must have been way wrong if it did happen. If this did happen, then the 650 that we thought the average was has got to be wrong, because we don't believe in things falling over here at 5.59 standard deviations. Okay? Now, the last thing I want to talk about is that whole big enough condition, and that's what we're talking about, the central limit theorem here. Okay? The central limit theorem tells us that as the sample size n gets bigger, okay, and bigger, right? As our sample size gets bigger and bigger and bigger and bigger and bigger, okay? No matter the original population is distributed, no matter how the original population is distributed, if n is large enough, the set of sample means is approximately normal. I'll say that one more time. No matter how the original population is distributed, as n gets larger and larger and larger, we will be big enough so that the set of sample means is approximately normal. And what we're trying to say is, let's just say that the population for the amount of money that students spend in Florida is actually skewed right. So most students spend some value amount down here, right? Very few students spend a lot of money when they're on vacation in Florida. Okay, so even if our population is skewed, when we start taking samples of size 20, so let's take a sample of size 20, another sample of size 20, another. We keep taking samples of size 20 out of here. The sampling distribution that represents what those samples of size 20 will look like will be normal. Why? Because remember, they're samples. So as long as we're taking a sample, yeah, we might get that occasional very high, throw it in there, but because it's so rare to have that very high number, it's going to even itself out. The other 19 scores are going to even out with that one. So again, the sampling distribution will be normal. And this is what the central limit theorem tells us. No matter the sample, no matter the proportion, right? No matter what this looks like, no matter what our population distribution looks like, the sampling distribution will be normal. Now, it requires that big enough means your sample size is, n is bigger than 30. So that's what we say is big enough. So as long as n is bigger than 30, then the central limit theorem kicks in and we say, who cares what the population looks like? The sampling distribution will be normal. So what do you do if you're under 30? If you're under 30, you better just cross your fingers and hope that the population is normal anyway. Because if the population starts off normal, then obviously the sampling distribution is going to be normal. So if you have a weird population distribution, then as long as n is bigger than 30, doesn't matter, the normal model is good to go. All right, and that's the end of the video. We're going to spend a lot of time in classwork on some of these problems, but hopefully you guys wrote down those formulas and took some notes because it's very, very simple.